Let us prepare a row measure formula and column measure formula for 4-dimension array. I'll show you the approach. Then using same approach, we will see a row measure, column measure formula for 3-dimensional array also. So here already I have an example of a 4-dimension array. Array name is A, data type is something, and the dimensions are D1, D2, D3 and D4. Now, for the address of any location whose indices are I1, I2, I3, I4, then what should be the formula? So let me prepare the formula for row measure. In 2-dimensional arrays already I have explained that row measure is done from left to right and column measure is from right to left. So we will go from left to right. So let us take, first is I1, the first index, into multiplied by, leaving first dimension, multiply rest of all the dimensions. So this is a D2 into D3 into D4. Now second index, that is I2. I2 is multiplied by, after dimension 2, all the dimensions should be multiplied. So this is a D3 into D4, dimension 3 and dimension 4. The next is index 3, I3. So the third index, I3, after third index. So after third dimension, all dimensions should be multiplied. So only D4 is there. Then plus, last I4, fourth index. After fourth dimension, everything should be multiplied. So nothing is there. So multiplied by W. This is the formula for row measure mapping of a 4-dimension array. So you might have observed what is the procedure for preparing the formula. So for every index, we take the dimensions after those dimensions. For I2, we take all the dimensions after D2. So this is the approach. We have taken it from left to right. Now I will write the formula for column measure. Column measure formula, address of, now for column measure, already I said that for row measure we go from left to right, for column measure we go from right to left. So let us prepare the formula. L0 plus, first one is index 4, so I4 multiplied by, see, this is dimension 4. So take all those dimensions before dimension 4. So D1, D2, D3. D1 into D2 into D3 plus. Now this one, we are moving from right to left. So next is I3, index 3. So go to dimension 3 and take all the dimensions before dimension 3. So this is D1 and D2. So multiplied by D1 and D2. Plus I2. I2 multiplied by, go to dimension D2 and take all the dimensions before that. So that is D1. Plus, this is I1 multiplied by W. So that's it. This is the approach for preparing the formula. Using 4-dimension, I have shown you how to write row measure formula and how to write column measure formula. Now using the same approach, we can write the formula for any dimensions, any number of dimensions. So even 2D was following the same approach, but this is a very small problem. So we have seen it thoroughly with the diagrams and everything. But here I am showing you directly the formula. Now based on this formula, by observing this one, we can prepare a general form of this one for n dimensions. So let us prepare a general formula for n dimensions for row measure mapping. So I am showing it for row measure mapping. Let us take same formula. I will generalize it for n dimensions. L0 plus, see, all these terms are added. See, this is one term, then next this is the term, next this is the term, next this term. So total 4 terms are there, 4 terms are added. So for addition we use sigma. And here I1, I2, I3 and I4 is used. So I and its subscript, that is I1, I2, I3. So I will call it as P. So P takes the values from 1 to, it is going up to 4. So instead of 4, just make it n. So this will be for n dimensions. So P takes the values from 1 to n, so for n dimensions. So this will become I1, I2, I3, I4 and so on up to n dimension. Next thing, every index is multiplied by dimensions. This I2 is multiplied by D3 and D4. So it is multiplied by product of dimensions. So this is a product of dimensions, So product of pi we can use of D. Now these dimensions are taking subscript from 2, 3, 4. So this is just 3, 4. So whatever I is, this is 1. So this is 2, 3, 4. So this is taking the values after P. So this is dq and q takes the values from p plus 1 to n. So it is going from 2 to 4, 3 to 4. So this is 2, so 3 to 4. This is 3, so 4 to 4. So q takes the values from p plus 1 to 4. And this whole thing should be multiplied with w. So this is the row major formula and general form of n dimension. So similarly, you can prepare a formula for column major mapping for n dimensions. So try this formula by yourself. Now let us do some analysis on this one. I'll remove this column major formula and we'll do analysis on row major formula. Let us see how many multiplications are performed for getting this result. Let us count them. 1, 2, 3. 3 multiplications here, 1, 2, 2 multiplications here and 1 multiplication here. Then that W is common always, that is plus 1. Depending on dimensions, the number of multiplications inside the brackets may vary. Now for 4 dimensions, how many multiplications are there? This is 3 plus 2 plus 1 for 4D. It means for 5D, how many multiplications will be there? So 4 plus 3 plus 2 plus 1. So for n dimensions, how many multiplications will be there? N minus 1 plus n minus 2 plus goes on to 3 plus 2 plus 1. So this is nothing but n into n minus 1 by 2. So n into n minus 1 by 2 is n square multiplications. Oh, these are too many multiplications. So the time taken for evaluation of this formula is n square multiplication operations. So this is too much time consuming. So the row major formula used by the compilers take order of n square time. So is there any way to reduce the number of multiplications? Let us see what we can do for reducing the number of multiplications. I will take only the portion of formula that is inside the brackets and I will write the formula from right towards left. This is the row major formula. I am just writing it reverse. So this is I4 plus I3 into D4 plus I2 into D3 into D4 plus I1 into D2 into D3 into D4. So I have taken only the portion of the formula that is inside the brackets and I have written from the last term onwards so that we can reduce the number of multiplications. So if you observe, this is having 4 values multiplied, 3 values multiplied, 2 values and then there is no multiplication. So I have taken from the smaller value onwards. So first is smaller, then go on increasing. Now in this, if you observe, this I4 is as it is plus D4, D4, D4. D4 is common among all these terms. So I can write D4 multiplied by, D4 is common, so I3 plus I2 into D4 is taken as common, so D3 is there, plus I1. D4 is taken as common, so this is D2 and D3. Okay, so I have taken common. So I got one multiplication here. Let us continue and see if we can take more common values. I3 plus. Now in these two terms, D3 is common. So I will write down D3 multiplied by and I2 plus I1 into D2. So I have taken D4 common and D3 common. Now only two terms are remaining here. Further, I cannot take anything common. This formula can be rewritten like this by taking dimensions as common. Now this is the same thing what is there inside the brackets. So let us see how many multiplications are there. This is 1, 2 multiplications, 3 multiplications. Oh, so for 4 dimensions, just there are 3 multiplications. For 4D, 3 multiplications are there. And for 5D, there will be 4 multiplications. So for ND, there will be n minus 1 multiplication. So total time for performing multiplications will be order of n. So this formula reduces the number of multiplication from n square to order of n. So by taking common, I have reduced the number of multiplications. So this is how we can reduce the number of multiplication in row measure as well as in column measure formula. So the rule that we have applied, that is taking commons to reduce the number of multiplication, this rule is called as Horner's rule. So we have applied Horner's rule to reduce the number of multiplications. So that's all with 4 dimension to n dimensions.